Okay. Hello, everyone. Today we are having a lecture about Maxwell distribution. A second, please. At the beginning, I would like to briefly remind what we have studied during the previous lecture. We have repeated some basics from combinatorics, especially permutations and combinations. Then I gave a brief introduction to the probability theory. It cannot be thought that this probability theory that I have introduced during the previous lecture is a rigorous one, because rigorous probability theory is complicated. In a sense, it's a very rigorous mathematical discipline. What I have told you during the previous lecture is some tentative introduction. So something like some kind of a simplified explanation which allows you to grasp the concepts lying in the probability theory, but it's not related to the rigorous theory itself. Nevertheless, we have studied the concept of probability for discrete events. So if we have a finite number of conclusions in our stochastic system, then we can introduce assign values which are called probability to all of these conclusions, to all of these events. And another concept was probability distribution for a continuous random variables. I have said that distribution of continuous variables in physics is presented by probability density function, which allows you to find the element of probability for the random variable x to be in a small interval from x to x plus dx. Then I have said that if your probability functions are defined correctly, they should obey some laws, and one of these laws is normalization. So normalization condition. Normalization condition can be written as follows for discrete probability distributions, so that the sum of probabilities for discrete conclusions or discrete events should sum up to give unity. And if you are dealing with probability density of continuous variables, then you should write that the sum is being transformed into an integral in the most general case from minus infinity to plus infinity of p of x dx. This integral should be also equal to 1. Today we are going to study Maxwell's distribution. This distribution was first derived by James Clerk Maxwell, the same person who invented modern electromagnetism theory. I think you have heard about Maxwell's equations in electromagnetism, 4 equations, which describe all of classical electromagnetic phenomena, including light generation and propagation. But the very same person has also solved the problem about the probability distribution of velocities of molecules in the gas. So if we have a vessel which contains large number of molecules of gas, we know that due to existence of temperature and thermal motion, all of these molecules are in a state of perpetual motion and a chaotic one. So they have velocities which are directed in every direction. So in order to describe this motion, we introduce a probability density for velocities. So let's call a function of velocity v which gives you the probability of some molecule to have a velocity in a certain small subspace in the velocity space. So first of all, you can think of a velocity space, so you can do the following. So we can introduce three axes and call them the x, vy, and vz. And for any molecule which has some velocity v, we can put to this molecule a point in this space which corresponds to components of this velocity when being projected onto different axes. Oh, maybe this one is. Okay. So that each of these molecules produces one point in this space. And then, by means of this probability distribution, you describe how many points have fallen into a small subspace in this space, into the small element of velocity volume. That is given by this function. The original idea of Maxwell is to determine this probability distribution, this probability density, using two assumptions. The first assumption is that the function, probability density function, should be independent of the direction of the velocity. Or so to say, this function should only depend on speed. And here I remind that while velocity is a vector-valued quantity, speed is a scalar quantity which is equal to the absolute value of velocity. And the reason for this is that the space is isotropic. So there is no chosen direction in space. So if you consider motion of molecules, there is no reason for a molecule to have this direction to be preferred over other directions. That means that all of the directions have the same rights. And for this reason, the probability density function should be independent of the direction of velocity. Or you can say that we can change the directions of axes x, y, and z, and when we change these directions, nominally vector v will change, but speed will remain constant. Isotropic space. And second assumption is less evident. The second assumption by Maxwell is that probability density function can be decomposed into three independent probability densities. So we can write that f of v dvx, dvy, dvz is equal to the product of three probability functions, phi of vx, phi of vy, and phi of vz, multiplied by dvx, dvy, and dvz. This means that this assumption says that motion along each of three axes is independent from each other. So you say that if we look at some particle which moves at some velocity v along axis x, that means that probability density for other components of velocity is not affected by Vx. So the probabilities for other velocity components are independent of Vx. Okay. While this assumption is less evident, well, I don't have a proof of this, but later we will see that actually, well, from other physical reasons, this assumption can be proven. And for now, let's assume that we have only these two assumptions. And let's consider what happens when we rotate velocity vector in space. So let's assume that this rotation happens in xy plane. So we slightly change velocity components in such a way that the total speed will remain the same. So we can say that f of v multiplied by dvx, dvy, dvz, which is equal to phi of vx, phi of vy, and phi of vz, dvx, dvy, dvz, should be equal to f of v prime dvx, dvy, dvz, which is f of vx prime, phi of vx prime, phi of vy prime, phi of vz prime multiplied by dvx, dvy, dvz. And when we consider this rotation, we assume that since v equals to v prime, so that initial speed equals to the final speed, that means that square root of vx squared plus vy squared plus vz squared equals to a square root of vx prime squared plus vy prime squared plus vz squared. Okay, we have vz prime here. But nevertheless, since we consider rotation in the xy plane, we can write that vz equals to vz prime. And from this follows that vx squared plus vy squared equals to vx prime squared plus vy prime squared. Or we can say that if we compare these two quantities, we can say that f of vx multiplied by phi of vy is constant when vx squared plus vy squared is constant. And this simple statement will allow us to determine this probability density function. Let me continue here. So let's look at the differential of this quantity. So let's write, or we can say that let's calculate a derivative of this with respect to Vx. And since Vx and Vy are connected to each other, that means that Vy can be considered a function of Vx. So we can calculate the derivative of this function using Chain's law. So what we have? We have phi prime of Vx multiplied by phi of Vy plus phi of Vx multiplied by phi prime of Vy multiplied by dVy over dVx as in Chain's law, and this should be equal to 0 because the derivative of constant is 0. And to determine this derivative, dVy over dVx, we calculate the derivative of the second equation here. That is, we have Vx squared plus Vy squared is constant. After we take a derivative of this, we have the following. 2Vx plus 2Vy multiplied by dVy over dVx is 0. From this, it immediately follows that dVy over dVx equals to minus Vx over Vy. And then we insert this quantity here. Now we have this. This can be considered as an equation which should be solved by means of variable separation method. Okay, in order to achieve variable separation, we need to have all quantities which contain Vx in one side of this equation, while all the quantities which contain Vy in the other side of this equation. To do this, first of all, we divide everything by phi of Vx, phi of Vy. And secondly, we also divide by Vx. So in the end, we have the following. 1 over Vx multiplied by phi prime of Vx over phi of Vx equals to 1 over Vy multiplied by phi of prime of Vy over phi of Vy. Since initially we have chosen xy plane rotation at random, it means that we could have also chosen rotation in xz plane or yz plane. So that means that similar equation holds for z component too. Also, since all of these quantities depend only on their own independent variables, that means that all of these are actually constants. So let's denote that this is alpha. Now we solve the following equation. So let's write this in Leibniz notation using differentials. And this equation can be easily integrated. So that means that finally this function phi can be found as okay. Looking at this function, we immediately see that if alpha is positive, then this function doesn't have any physical mean, because that means the probability density for some molecule to have insanely huge velocity increases with the velocity. So when we have positive valued coefficient alpha, that means that literally these molecules move at an infinite speed. And this probability density function cannot be normalized, because integral from minus infinity to plus infinity of phi of Vz multiplied by dVz is infinite. That means that positive alpha cannot describe any kind of a physical condition. So that means to achieve some physically reasonable result, we should assume that alpha is negative. Or in short, we can write, since we are not at this point, since we are not constricted, we don't have any constrictions on how we choose coefficient alpha, we can write that phi of Vz is actually some constant, which, as you should understand, this constant is a normalization constant. So this constant can be determined from normalization. Multiplied by exponent of minus alpha Vz squared. And similar equation for any component of velocity, phi of y and phi of Vx. So now we have derived Maxwell's distribution. This distribution is called Maxwell distribution, but this formula is a bit different from what you would see in textbooks, because it doesn't contain temperature and it doesn't contain anything related to the thermodynamic properties. So we only have that there is some exponent, there is some coefficient here, but the relation between this coefficient and temperature is yet unknown. So in order to understand the relation between coefficient alpha and actual properties of the system, we need to consider some physical interpretation for this result. So for example, we should use this probability density function in order to calculate pressure exerted by a gas onto the side walls of the vessel which contains the gas. So here we choose a small area of the side wall of the vessel, and then we surround this area by imaginary surface. And this surface is cylindrical surface, so if the area looks like this, then this surface should follow the shape of the chosen area. So we choose it like this cylinder. And then we calculate, using this probability distribution, the pressure exerted by gas onto this area. For simplicity, we assume that the height of this cylinder H is very small compared to characteristic size scale of this area. This is assumption. Okay, and for now let's look at the momentum of particles contained within this area. So let's assume that outside this area we don't have gas, so everything here is a side wall of the cylinder. So only particles of gas can be found inside the vessel. And now let's focus on the momentum of these particles. And especially, what we need to especially have our focus on is the momentum projection onto axis which is normal to this area. So let's say that this axis is called x, and we are interested in a projection of momentum of all particles onto this axis. So we can write that this momentum is sum of momentum of each of the particles which are located inside this surface and their projection onto this axis. Well, of course, since we have some stationary probability distribution, that means that on average, if you look at this quantity over time, of course this quantity would fluctuate, but on average, the average projection of momentum onto this axis should be constant. But now let's look at what kind of external conditions affect this momentum, this average momentum. First of all, momentum inside this area is affected by three phenomena. The first phenomena is when a new molecule enters, crosses the surface. So a new molecule crosses the surface. And so new molecule gets inside, so it gets into this volume. Surface into the volume, into the selected volume. So when a new molecule appears, that means that that the sum of this momentum, sum of this momenta, increases by the momentum of the new molecule. So if new molecule crosses, that means that delta Px equals to the mass of the molecule multiplied by the projection of the velocity onto x-axis. So the second phenomenon is, of course, when the molecule escapes the selected volume. So if molecule escapes, that means that the molecule leaves through this surface, and that means that actually the velocity projection onto this axis is negative, and when molecule escapes, then delta Px should be equal minus m multiplied by the x. But since the molecule is escaping from this volume, that means that this velocity projection is negative, and that means that delta Px also increases when molecule escapes. So delta Px increases then when new molecule gets into the selected volume, and Px also increases then when molecule escapes. But in order to stabilize, in order to achieve the balance of momentum, in order to achieve constant momentum in the selected volume, we need to have another process which affects momentum of particles in the selected volume, but is not related to molecules escaping or coming into the selected volume. This process is collisions with the side wall. In our consideration, we will not say that these collisions are, let's say, exactly follow the mirror rule. So we do not assume that when molecule collides with the side wall, that x component of the velocity changes its sign. So we can also assume that side wall, for some reasons, is also engaged in thermal motion, and for this reason, after the collision, the velocity, the x velocity component of the molecule can be equal or can be less or can be higher than the initial x velocity component. So here we don't have any kind of assumption related to the nature of collisions with the side wall. Because, as we know, side wall also is engaged in thermal motion. But nevertheless, if the pressure exerted on the side wall is equal to some quantity P, that means that due to this pressure, on average, delta Px divided by delta T equals to minus pressure multiplied by selected area, so the selected area, and that is it. So this is the force exerted by the side wall onto the gas, and here is the change of momentum produced by this force. And this change of momentum is negative. So that means that while two first processes produce positive changes of momentum, the third process produces negative change of momentum, And altogether, all three processes produces, so they balance each other. So positive valued processes are balanced by the negative valued process. So in order to calculate the pressure exerted by a gas onto the sidewall, we need to calculate these positive valued processes. So in order to do this, we divide all of the molecules into subsets. So let's say we have a large set which contains all of these molecules, and we can divide this large set of molecules into subsets. And I call each subset S of Vx. So let me say that S of Vx is a subset of molecules whose x velocity component falls in this interval. So falls in the small interval around some velocity projection. So you can even say that the number of such molecules equals to the total number of molecules multiplied by phi of Vx multiplied by dVx. And if we divide this number by volume of this vessel, we get a number density of such molecules related to the total number density of molecules in the vessel. So let's look only at such molecules. Let's look on some subset S of Vx. Of course, we have many of such subsets with different values of Vx. But let's first consider only one of them. The number of molecules entering. So if Vx is positive, then it means that such molecules can enter the selected volume. That means that the number of such molecules entering the selected volume can be found as follows. So let's say this is a surface which separates the selected volume from the outside volume. And let's say that there is such molecule outside of the selected volume, and it moves with the x component of velocity along this axis. So, and we have many of them. So let's say we have dn, the number density of such molecules equals dn. Then the number of molecules entering the selected volume can be found as follows. Let's look over a small amount of time dt. And if we look at small amount of time dt, then we can separate the molecules which enter the selected volume during this amount of time dt from those which don't enter. If initially the molecule is at a distance x from this surface, and this distance x is less than Vx dt, that means that after amount of time dt, this molecule will be inside the selected volume. But if this distance x is larger than Vx dt, then this molecule remains outside. So looking at this, we next do the following. So if we choose some direction, we can make a small cylinder, again a small cylinder, whose height equals to Vx dt. And if molecules moving in this direction are located inside this cylinder, they get into the selected volume. But if they are located outside of the cylinder, they don't get inside the selected volume. So, and then we can easily calculate the number of molecules which enter per unit of time. So dN over dt, number of molecules entering the selected volume per unit of time, can be found as dN, which is number density of molecules having x velocity component in a small range from Vx to Vx plus dx, multiplied by the volume of this cylinder. And the volume of this cylinder equals to dA multiplied by Vx dt. Okay, since we have divided by dt, then I don't write dt here. So the number of molecules dN is d small n multiplied by dA multiplied by Vx multiplied by dt. Then if we divide it by the small amount of time dt, we get the number of molecules entering the selected volume per unit of time. So you see actually the frequency the frequency of events of molecules entering the selected volume. So when these molecules enter the selected volume, they change the total momentum inside the selected volume per unit of time as follows. We need to multiply this quantity by mvx, by the momentum which is carried by each of these molecules. So then I do the following. dN multiplied by dA multiplied by Vx multiplied by mvx, momentum carried by these molecules. Okay. And everything here is for Vx greater than 0. Now let's consider the molecules which escape from the selected volume. So this was the result for N, for the first of these processes. And as you see, actually the second phenomenon can be analyzed in the very same manner. So we can repeat all of the same line of thought in order to get the final result. Again, delta P over delta T, so the increment of momentum per unit of time is dN multiplied by dA multiplied by Vx multiplied by mVx. But here, Vx is negative and mVx is negative, and altogether we get positive increment of momentum. And then we compare it with this. So we add the contribution from pressure. Okay. So this is actually the contribution to momentum increment from molecules from one of the subspaces. In order to get the momentum increment from all of the molecules, we should integrate the contribution from each of these subsets of molecules. So that means that after I sum up this and this, I get for increment of momentum per unit of time the following formula. N multiplied by phi of Vx multiplied by dA multiplied by mVx squared by dVx and integrated from minus infinity to plus infinity. So I can take n, m, and dA from this integral, since they are constants with respect to dvx, and have this n dA, okay, m multiplied by n multiplied by dA multiplied by the following integral. If you look at this, this is actually the average square x component of velocity. So I can write that this is n multiplied by m multiplied by Vx squared average multiplied by dA. And from our previous considerations, we know that this should be equal to PdA. From this I find the pressure. Pressure is n m Vx squared average. So this equation can be considered as one of the main equations of molecular physics. It relates the pressure exerted by the gas onto the side wall of the vessel, and it relates this macroscopic value, which is pressure, to the microscopic value, which is the average square of velocity. Now we need to calculate average square of velocity component. And this is a pure mathematical task. We need only to calculate an integral. So according to the definition, average value of Vx squared is given by the integral from minus infinity to plus infinity of Vx squared multiplied by phi of Vx multiplied by dvx. Then I can insert this function into this definition. So this is according to the definition of average. And next we use this. So let's say we denote this equation by asterisk, which is Maxwell's equation, and here we use this asterisk here. So minus infinity plus infinity Vx squared times exponent of minus alpha Vx squared dvx and multiplied by normalization constant. But we don't know normalization constant yet. So, but we know that the integral of c multiplied by exponent minus alpha Vx squared dvx, according to the normalization condition, should be equal to 1. And from this, we immediately get that this is a reciprocal of integral from minus infinity to plus infinity of this exponent. So here we can write, instead of normalization exponent, we can divide this integral by this integral. Okay, for now we stop at this point. And as you see, in order to work with Maxwell's distribution, we need to have some method for calculation of these integrals. So in a general case, we actually need a method to calculate integrals of the following type. So we need to calculate integrals of the following type. Integral. Okay, let's do integration from 0 for infinity for reasons I will tell you immediately. Of v to the n multiplied by exponent of minus alpha v squared dv. And we call this integral f of n. Why do we do this from 0 to infinity? The reason is quite simple. If n is odd, that means that the integral from minus infinity to plus infinity of v to the odd power multiplied by this exponent times dv is an integral of an odd function. And when we do this from minus infinity to plus infinity, the total integral should be 0. So that means that integral from minus infinity to plus infinity for n being odd doesn't give us any kind of useful information. But the integral for positive valued v's for the odd n is some meaningful quantity. For this reason, I do integration from 0 to infinity. But here we have integrals from minus infinity to plus infinity, in this case. But we can easily express these integrals for even values of n. So when we do this integral from minus infinity to plus infinity for even values of n, okay, it's actually twice the integral from 0 to infinity. So that means this is twice f of n. And since we have ratio of these two, we can write that for this expression here, we can write that this is actually equal to twice f of 2 divided by twice f of 0. This is f of 2 over f of 0. The next part is how we calculate these f's. It's only mathematics here, but this mathematics is strongly related to Maxwell distribution. And if you are able to implement this mathematics during the problem solution, it will help you to find the answer very quickly. Okay, so how we do this? Let's calculate a derivative of f of n with respect to alpha. So alpha here is a parameter of the integral, and we calculate a derivative over this parameter. In this case, we can take the derivation operator inside the integral and get the following. So this is actually minus alpha multiplied by f n plus 2. So that means that if we know f of n, we can determine f of n plus 2 by simple derivation operation, so by taking a derivative of f of n as a function of alpha. Now let's look how these functions depend on alpha. So let's say, let's perform the variable substitution. So let's substitute variables. So let's say f of n of alpha is integral from 0 to infinity of v of to n multiplied by exponent minus alpha v squared dv. And here we insert a new variable. Let's call this variable, for example, y. And this variable being equal to v square root of alpha. Then, from this variable substitution, we can get that v is y divided by square root of alpha, while dv is calculated as dy over square root of alpha. Now we insert these v's and dv's into this integral. And of course, when we do this substitution, when v equals to 0, then y also equals to 0. And when v equals to plus infinity, then y also equals to plus infinity. That means that there is no change in the limits of integration. And here we have y over square root of alpha to n, exponent of minus y squared multiplied by dy over square root of alpha. And this is actually, I take all of these square roots of alpha out of this integral and have the following: 1 over alpha into n plus 1 over 2 multiplied by integral from 0 to infinity y into n exp minus y squared dy. And this is the same integral as in the beginning, but for alpha equals to 1. So this is f of fn of 1 over alpha multiplied by n plus 1 over 2. So divided by alpha to n plus 1 over 2. So this is the dependence of f on alpha. And when we do this derivation, so when we take a derivative of this function, we can treat this one as a constant. So that means that dfn over d alpha is fn of 1 multiplied by derivative of alpha to the minus n plus 1 over 2. So this is minus n plus 1 over 2 multiplied by alpha to minus n plus 3 over 2 multiplied by fn of 1. And then we look at this, and from this we get fn plus 2 of alpha. Okay, finally, here, here I can write that f n plus 2 of alpha is minus fn prime of alpha over alpha. And then for the derivative, I insert that value. So that gives us n plus 1 over 2 multiplied by alpha to the power minus n plus 3 over 2 multiplied by fn of 1 and again divided by alpha multiplied by alpha to power minus 1. Okay, so now I can do some kind of variable collection. So from here we know that fn of alpha is equal to this one. So for fn of alpha is equal to this one. And that means that we can look at fn plus 2 of alpha as this. Fn plus 2 of 1 over alpha to the power of n plus 3 over 2. Okay, there is some kind of mistake here. Let me determine where it is. So now I have this one. When I take a derivative here. Okay. This alpha should not be here. Now it works. Since there is no alpha here, so when we take a derivative with respect to alpha here, exponent gives me exponent, and v squared is a coefficient in the exponent, and v squared gets multiplied here. And there is no alpha in that expression, and that means that we have this type of a result. So that means that f n plus 2 of 1 is fn of 1 multiplied by n plus 1 over 2. So now we have a recurrent expression which allows you to determine fn plus 2 from fn. And that means that in order to get all of the values of this fn, we need only to calculate this integral for n's which are equal to 0 and to 1. Now let's do this. So let me look how much time do we have left. Okay, we have some more. So we need to calculate these two integrals. Okay, first f of 0. F of 0 at alpha equals 1. This is the integral of x minus v squared multiplied by dv. For this integral, there is a common trick which allows you to find this integral. We introduce a second variable. So let's say that let's call this x. And let's write that this integral can be found as square root of integral of x minus x squared dx from 0 to infinity and here from 0 to infinity, multiplied by an integral from 0 to infinity, x minus y squared dy. And then we can look at this and treat this as an integral in two-dimensional space. So we integrate over the first quarter of xy plane, and we integrate x minus x squared plus y squared multiplied by dx dy. And as we can see that this can be found using transformation to polar coordinates. This is square root of x, so integral from x minus r squared, and here dx dy is substituted by pi r over 2 multiplied by dr. So here we have this. We can take, okay, and r changes from 0 to infinity here. And then we do this integration as follows. X minus r squared. And here, this is pi dr squared over 4. So this is square root of pi over 2 multiplied by square root of integral from 0 to infinity x minus r squared dr squared. This integral is easily calculated. This is a simple exponent, and the result is 1. So that means that the final result is square root of pi over 2. This is f0 of 1. f1 of 1 is similar, except that we don't need to use this trick, because we can immediately calculate integral. For n equals to 1, the integral is f1 of 1 is from 0 to infinity x multiplied by exponent minus x squared dx. This is actually from 0 to infinity exponent of x minus x squared dx squared over 2. Again, a very simple exponential integral. We take 1 over 2 outside, and this integral equals to 1. So f1 of 1 is 1 over 2. Now, based on these two quantities, we can determine everything here. But actually, in order to calculate Vx squared, we don't even need to know the value of f0 of 1. Because we need to calculate the fraction of f2 to f0, and according to this expression, we know that is n plus 1 over 2, but if we include, so if we calculate this expression for any alpha, so if we calculate the ratio for any alpha, we need also to take into account this factor. So I have here n plus 1 over 2 coming from this ratio, and also I have an additional factor alpha which comes from ratio of these denominators. So here, if we have n plus 2, that means that this denominator is greater, so that means I divide this by alpha. Okay, so this ratio is n plus 1 over 2 alpha, and for n equals 0, I have 1 over 2 alpha. 1 over 2 alpha. So this is the average square of velocity. I inserted here I get that pressure equals to number density of molecules multiplied by mass of each molecule and divided by 2 alpha. I should compare this with the results available from thermodynamics. As I know from thermodynamics, for any ideal gas, PV equals to nu RT. I can divide this by volume and get that P equals to, and nu is m, the mass of the gas divided by molar mass divided by volume multiplied by RT. This mass divided by volume is density of gas. And this density, we can write it as follows. This density is product of N, which is actually N, which is number density of molecules, multiplied by mass of each molecule, M, Nm. Here, RT over mu. So now I compare this expression with this expression. And from this I find that 1 over 2 alpha equals to RT over mu, from which alpha is m over 2RT, mu over 2RT, where mu is molar mass. Or if we express this in variables related to a single molecule, we can write that this is a fraction of mass of one molecule divided by 2 multiplied by Boltzmann constant K multiplied by T. Here I have used, when I get from this to this, I use two simple properties of molar mass and universal gas constant. This is mu is equal to the product of Avogadro number and mass of each molecule, because in 1 mole of gas we have Avogadro number of molecules, while R is the product of Avogadro number and Boltzmann constant. Boltzmann constant is equal to 1.38 times 10 to the minus 23. So this is units Joule over Kelvin. This is Boltzmann constant. And that gives us the final formula for Maxwell distribution in the following form. That phi of Vx is normalization constant multiplied by exponent minus mvx squared over 2kt. Finally, we can write it like this, where Ex is a kinetic energy along x-axis. The derivation of Maxwell distribution is finished. And also, please remember, so I will give a brief conclusion to lots of this material. I will write down on one blackboard everything that you should know. Well, I have deleted something interesting. So this is everything about these integrals. Oh, well, not everything. I can also add this one. Okay, this is about integrals, and about pressure. I have n multiplied by Vx squared. Good, so far so good. So this is everything that we have derived during our previous time. Next, I would say that this is not the end. So initially, I have also introduced that Maxwell distribution is given by this formula. So if I take this normalization constant as C, I get the following result. And after I sum up all of these contributions to the kinetic energy coming from each of the axes, I get C cubed multiplied by exponent minus kinetic energy over kT. Very simple formula for Maxwell distribution for kinetic energy, where kinetic energy epsilon of one molecule is given by this expression. Okay. Next, the formula for pressure is there. Next, we are going to consider another distribution. So we have derived Maxwell distribution for velocities. The next coming is Maxwell distribution for speeds. It's a bit different distribution from distribution of velocities. So for the distribution of velocities, we have the following. The probability element is equal to C cubed. Okay, we can write proportional to exp minus E over kT multiplied by dvx, dvy, dvz. Now let's, for simplicity, consider two-dimensional space. We have Vx and Vy. So we randomly drop points onto this plane following this distribution, so that more points are being accumulated along, near the origin, and less points are far from origin. Next, we need to transform this probability distribution, probability density function, into probability density function for speeds. So speed, as I have said previously, speed is absolute value of vector of velocity. So for the speed, we can say that if we have these two circles, one circle with radius v, and the thickness of this circle rim is dv, then all of the points which have been dropped into this circular rim will contribute to the number of molecules which have speed in between v and v plus dv. So for the probability distribution for speeds, we need to multiply this probability density by the area of this circular rim. And this area is, so I can write it, this is c cubed, so c is a normalization constant from previous expressions, multiplied by exponent of minus e over kt, and I need this to multiply this by area of this circular rim. So I multiply it by 2 pi a, 2 pi v multiplied by dv. But this is for two dimensions. If I consider 3 dimensions, then instead of a circular rim, I have a spherical layer, and I can write that probability density for a molecule in 3-dimensional space, okay, here is to have a speed between v and v plus dv is equal to c cubed multiplied by exponent of minus kinetic energy over kt multiplied by 4 pi v squared multiplied by dv. So I can introduce a new function, let's say g of v, which stands for probability distribution for speeds, which is c cubed multiplied by exponent minus mv squared over 2 kt multiplied by 4 pi v squared. And this probability distribution function for speeds behaves somewhat differently from probability density function from velocities. So let's see how different this behavior is. Okay, let's look at probability density as a function of Vx. We have exponent minus mvx squared over 2kt. So that means that we have some kind of, so this is a normal distribution. You can Google it, normal or Gaussian distribution. The maximum value in this distribution is 0. The average value is 0. And we have a variance in this function. But if we look at distribution for speeds, a function g of speed v, we need to multiply this exponent by v squared. And that means that when v approaches 0, this function is actually 0. Then it rises, but at some time this exponential overtakes this power law dependence. As you know, that when you go to infinity with v, then exponential dependence always overtakes power law dependence. So that means that if we increase velocity after some rise, we reach maximum and then decrease. And more importantly, this probability distribution function is not symmetric. Here there is a symmetry. The distance from this point is equal to the distance to this point. In case of probability for speeds, these two distances are in general different. So now let's do some few simple calculations. Okay, we are almost out of time. So a few simple calculations. First of all, with this probability distribution function, the average speed is v multiplied by g of v multiplied by dv. It can be written as integral from 0 to infinity. So here we have v cubed, because v squared comes from function g and v comes from this factor, multiplied by exponent minus mv squared over 2kt dv. And in order to not to mess with this normalization factor, I divide it by v squared exp minus mv squared over 2kt multiplied by dv. Okay, so this is actually, what is this? So if you look at these integrals, this is f3 of m over 2kt divided by f2 of m over 2kt. So now we use these formulas. For f3, we know that this f3 is equal to f1 multiplied by 1, or actually here by 1, f1 of 1, and then divided by alpha to power n plus 1 over 2. So 3 plus 1 over 2 gives you 2. So over alpha squared, alpha is m over 2kt. So that gives me m over 2kt squared. And for the bottom integral, we have f2, and f2 can be expressed as f0 multiplied by 1 over 2. And again, divided by alpha. So here 2 plus 1 over 2 gives 3 over 2. So we divide by m over 2kt, 3 over 2. Then we insert all of these values. f1 of 1 is 1 over 2. f0 of 1 is square root of pi over 2. This is m over 2kt to power minus 2. Here, m to 2kt to power minus 3 over 2. So, altogether, these are cancelled out. This gives me 2 over square root of pi. And this gives me m over 2kt to the power of minus 1 over 2. So 8 kt over pi m. This is the average speed for molecules. Next is average squared speed for molecules, but this can be determined from previous considerations. So previously we have found that Vx squared average is equal to kt over m. So that means that V squared average is 3 kt over m. You can also do this independently using this integral, so using the speed distribution. And the next important quantity for Maxwell distribution for speeds, so this is Vx, and we know that V squared is actually equal to sum of Vx squared plus Vy squared plus Vz squared. As each of these squared quantities equals to kt over m, because these quantities should be independent of the axis. So Vy squared should be equal to Vx squared, because this quantity should be independent of the direction of the axis. So this is 3 Vx squared average. That gives me 3 kt over m. And the most probable speed can be calculated as here. Most probable speed corresponds to the maximum of g of v. So the speed at which this distribution function reaches its maximum. And to determine this, I calculate a derivative of this with respect to v, and when this derivative equals to 0, then yes, we get the speed at which this quantity is maximum. But for simplicity, I insert this v squared into the exponent and consider this exponent. So this exponent is minus mv squared over 2 kt plus 2 logarithm v. Now I take derivative from this exponent and get, so I take derivative, I get mv over kt plus 2 over v, and here minus is 0. So that means that here I have mv squared over 2 equals to kt, and that gives me the most probable speed as 2 kt over m, square root of 2 kt over m. Well, I think with this we should conclude our lecture today because we don't have enough time. We have some questions that we have not touched during this discussion. One of the questions is the number of collisions. Number of collisions with a unit area of sidewall. And another question is average energy of a fusing molecules. So there is a process which is called effusion. To do this process, we do the following. We have a vessel, and we poke a small hole in this vessel, a very small hole, and then look at molecules which escape from this vessel through this hole. The main condition for this hole is that this hole should be small enough in order to prevent formation of stream. So as we have studied previously during our hydrodynamics, that if we have a large enough hole, then we have a stream of gas escaping from the vessel. But here we make this hole so small that molecules escape through this hole without forming a stream. So they escape by means of like ballistic molecular motion. So they just escape and they don't affect each other. So they don't collide inside this stream. So they don't collide in the vicinity of this hole. And this prevents the formation of stream. So this process is effusion. So the gas escape from a very small hole. I think we are going to discuss this question during this seminar. Okay, thank you for your attention. I think with this, I'll end this lecture.